Welcome to The Explainer. You know, the world can feel, well, pretty chaotic, right? Unpredictable. But what if I told you there's a way to find some order in all that chaos? Well, today, we're going to build a toolkit to do exactly that. We're diving into the principles of probability, and we'll be using the work of Professor Dirk Crozier as our guide.
So we're basically surrounded by what mathematicians call random experiments. All that really means is situations where you just can't predict the exact outcome. Think about something super simple, like tossing a die. You know what could happen, right? A 1, a 2, up to 6, but you have no idea which one it's actually going to be.
Or we could be talking about something with way higher stakes, like, say, the reliability of the engines on an airplane. The performance of each one of those engines, that's its own little experiment with an uncertain outcome. And yeah, understanding the probability of one failing, that is absolutely critical for keeping everyone safe.
And this idea, it extends to the natural world too. I mean, trying to predict the exact amount of rain we'll get next month, that's another classic random experiment. Even with all our amazing weather tech, we can't nail down the exact number in advance. But, and this is the key, we can analyze all the possibilities.
All right, so let's get into it. Here's what we've got on tap. First, we'll nail down what a random experiment actually is. Then, we'll get the lingo down, the language of chance. After that, we'll see why just counting is one of the most powerful tools we have. And to wrap it all up, we're going to test our new skills on a famous puzzle that trips almost everyone up, the birthday problem.
Okay, first things first. Before we can even start to analyze all this randomness, we've got to have a solid foundation. So, what exactly makes an experiment random to a mathematician?
And here's the answer. A random experiment, it's not just any unpredictable event. Yeah, the outcome is uncertain, but, and this is the really important bit, the collection of all possible outcomes is something we can actually analyze. It's like a bridge connecting total chaos to some kind of structure. So how do we do that analysis? Well, we need to be speaking the same language, and the language of probability gives us this really precise vocabulary, and it's built on 3 essential building blocks. First up is something called the sample space. Think of it as the complete map of everything that could possibly happen. So if you're rolling 2 dice, the sample space isn't just the sums, 2 through 12. No. It's all 36 possible pairs, from rolling a 1 and a 1 all the way up to a 6 and a 6.
Next, we have what's called an event. Now, an event isn't just one single thing happening. It's any specific outcome or group of outcomes that we're actually interested in. For example, the event that the sum of 2 dice is 10, well, that's a little group containing 3 specific outcomes, a 4 and a 6, a 5 and a 5, and a 6 and a 4.
And the last piece of the puzzle is probability itself. It's really just a rule, a way of assigning a number between 0, meaning impossible, and 1, meaning it's a sure thing, to any event. One of the most important rules is the sum rule. It basically says if 2 events can't happen at the same time, the probability of one or the other happening is just their individual probabilities added right together.
And this is so cool, because it really brings that first building block to life. This table you're seeing, that is the sample space for rolling 2 dice. Every single one of those 36 boxes is a unique possible outcome. And when you see it laid out like this, it becomes super obvious why rolling a 7 is way more likely than rolling a 2. Just look, there are 6 different ways to get a 7, but only one way to get a 2.
And that leads us perfectly into our next big idea. Now that we have the vocabulary down, we need the most important tool in our entire toolkit for a lot of these problems: the simple but incredibly powerful art of counting.
And this is why counting is so important. There's this thing called the equally likely principle. It just says that if all your outcomes are equally likely, like with a fair die or a fair coin, then figuring out the probability is surprisingly simple. You just count up the outcomes you care about, your event, and divide by the total number of outcomes possible. That's it.
But, okay, counting can get really tricky, really fast. So to make things easier, mathematicians have this clever trick called the urn metaphor. Weird name, I know, but basically any counting problem can be thought of as drawing balls from an urn. You just have to ask 2 questions. 1, does the order I draw them in matter? And 2, do I put the ball back after I draw it? Answering those gives you 4 different situations that cover a ton of different problems.
Okay, so our toolkit is built. We've got the language, we've got the counting framework. So now, let's turn this thing on and test it out on a problem that is famous for messing with people's intuition.
So here's the question for you. Picture a room with 40 people in it. What do you think the probability is that at least 2 of them share the same birthday?
And let's keep it simple. Forget leap years, just 365 days. What's your gut tell you? Is it low? Maybe, I don't know, 20%? 30%?
The actual answer is a whopping 89.1%. Yeah, it is almost a sure thing. And that result is so counterintuitive for most of us, right? It's the perfect example of why we need these formal tools of probability. Our gut feelings about chance, they can be way, way off.
And this chart really shows you why that number is so high. The probability just climbs incredibly fast. Look, with just 10 people in a room, the chance is already over 11%. But the real shocker is at 23 people. That's the tipping point where the probability actually crosses 50%. It's officially more likely than not. And as you see, by the time you get to 40 people, it's pretty much a done deal.
So here's the big takeaway. Probability is so much more than just a way to figure out the odds in a card game. It's a whole structured way of thinking. It's like a reality check for our own intuition, which, as we just saw, can be pretty flawed. It gives us this reliable way to think about uncertainty and, a lot of the time, uncover truths that are really, really surprising.
And that leaves us with one last kind of mind-bending question to think about. We started this whole thing talking about random experiments, but we just walked through how we can build these really precise mathematical models to analyze and even predict how they behave. So that leads to a pretty cool thought. If we can model it with this much accuracy, is any of it really truly random to begin with?